Hello everyone. My name is Dr. Sampath Dikal and I'm covering today query processing and query optimization under the module Advanced Database Systems. So in my presentation, I'm going to talk about two parts. The first part is query processing part, which means we talk about how, given a query SQL statement, we need to identify what exactly that query statement is. There are different activities or the function is there we need to identify. For example, when you use select from where statement, we can use select statement to filter out the attributes. When we use from, we talk about what database tables that we want to access, right? Where we can use to filter it. So similar to that, we need to discuss how exactly query is processed. Now, in that process, we will identify what are the basic operations. So when you talk about the basic operations, we are going to relate this to relational algebra, which you have learned in the database course. So we are going to relate that to relational algebra. And by doing so, in the second part, we can talk about optimization. So how do you optimize your query? And what are the techniques, database management system uses? That's the topic for us to discuss. So having said that, let's start discussing this. Right. In graphical terms, the query processing we can represent in this way, starting from a query in high-level language like SQL statement. Let's say we want to extract or we can get all the employees from our company database. So company database means, if you remember, in our database Namate's book, this is the example we are discussing from the beginning. So this particular data set is about a company where there are like, several employees works for a company and they belongs to a set of departments and they do projects. The department supervise or controls the project, and then employees are working on various different types of projects. And the companies keep track of employee dependents as well. So given this, if you want to, select only employees, then we can refer employee table and we can write SQL statement saying that, okay, select all from employee, which will give us all the employee details. Similar to that, if you want to get employees and their project details, that means we want to combine employee with project. That means we have to get the connections through the works on. So we know each of the employee works for different projects. So we need to connect three tables now: employee, works on, and a project, right? So when you want to connect three tables, you have to have two join operations. So we can say select all from employee, works on, project, where we can say, okay, we can connect social security number to employee social security number, and then project number to P number in the project, so that you can get the required results. Now, the question is how exactly this will be processed when you're writing a SQL statement. So you can have a SQL statement here. So the first one is when you want to optimize your query, the database management systems try to identify what this particular query is. So it uses different techniques, scanning, parsing, and validating to identify what the query is about. Then the next one is once you scan, parsing, and validating, you will get what we call immediate form of the query. Then we know like what data structures I have used where we can optimize the query. So when you're optimizing, you are selecting different data structure to acquire the data. Once you do that, then we can formulate the execution plan, which will generate query code generator. And then code is execute the query, which will affect the runtime database processor. And finally, we get the result. So having seen this, when you want to translate SQL queries, we need to understand the intermediate representation. So that's the reason why we have learned relational algebra in your previous database course. So what happens when you use a SQL query? First, it will translate into a relational algebra expression. And then once you do that, we can represent these expressions as a tree data structure, or it could be a tree or a graph. Then you can identify different blocks, and each of these blocks you might see select from where close. So you can identify the different blocks. So if you have a nested query, that means you have two queries together, right? We can make it as a separate blocks. Now we use a term query tree. So let's try to understand what query tree is. So query tree is includes the relational algebra operations and data structures for internal representation when you perform a query. Right. So when you look at relational algebra operations, let me briefly review what you have learned so far. I hope you have already done this part in your previous database management systems module, where the select operation in SQL we represent in relational algebra using sigma notation. And then within this, with the sigma, we talk about list of attributes, and then we specify relation. Now, when we say, for example, let's say I want to get employee first name and last name. So we can write, okay, select, we can say first name and last name, we'll say F name. We'll say F name and L name, because selects will list the attributes that you need. And then we will have the relation, let's say employee. So what happens in this query, according to relational algebra, we actually requesting first name and last name of employee. And this is what we can use. Okay, sorry, I made a mistake here. It's project operation. Let me not confusion this one. So this should be project. That means we are selecting only we are going to select, or we keep only the first name and last name. But for example, if you want to select where if you need all the employees whose salary is greater than 40,000, then we can use a select operator. So we can say select, we can say salary, let's say greater than 40,000. and employee. So it will filter out the records, right? So that is called condition. So what we get here is from the employee relation, we get all those reports whose salary is greater than 40,000. Whereas here, we select a set of attributes. Similar to that, you might have also discussed joint operations. We can talk about how to combine two relations, such as employees with the department. You can list the joint condition, right? And there are different types of joints we can talk about. If you have check for equality, we can have equijoint, or you can, if you have same attributes in the two relation, then we can use natural joint. Then there are other, set operators like union. You combine two sets of results together, and then you get, common results for both relations R1 and R2. Then we can also have difference where we will have all the records belongs to R1, but R2. All possible combination, we use Cartesian product, and this might not be the valid relation. And then finally, you can use division operation. So those are the relational algebra operations you might have learned so far. Okay, now let's move. So having we reviewed what we have for relational operators, right? Now, the first thing is, given a particular query, we should be able to, right, understand how this will be written in both SQL as well as in relational algebra. So given our data set, maybe you can take a screenshot of this. So I will go back therefore, right? Can you take a screenshot of this? Okay, anyway, I have copied and I'm going to share in the chat. Right. Okay, now based on that, can you give me the SQL statement to answer this? Okay, so I got an answer from Ishan. Thanks, Ishan, for sharing your answer. So you can notice that we are using select, from, and where clauses to answer this question. And if you notice, when you want to, answer this one, we want to connect multiple tables, right? So we want to connect the project table, department table, and then employee table. So since we are connecting with three tables, we have two joint conditions and one selection. That means it should be project location from Stafford. And what we need to retain is project number, controlling department name, or controlling department number, and department manager last name, address, date of birth. Right. Okay. So let's see its equivalent relational algebra expression. To look at its equivalent relational algebra expression, right? So you can see here we are connecting three relations. When it comes to relational algebra, we say relations. We connect with project, department, and employee. And you can see the connections. The project and the department will connect using department number and department number. And then result will connect with the employee, where we have manager social security number should be equal to social security number. And the next is you need to make a selection. In the selection, we say project location should be Stafford. And we want to select only project number, department number, last name, address, and the birthday. Right. So now the next thing is we need to understand how we may represent as a query tree. Now, when I say query tree, we have to separate out how these operators are connected to each other. So there are several operators here, right? We have a select operator. That means this one, project operator, then all these join operators, right? Let me give you one example. So if I look at one example, it's looks something like this. Okay. So if I read from the beginning, it goes from the bottom to top. So first one, we can connect both project and the department. And in this particular case, the first of all, we will select only the projects in Stafford. And then we connect both the department and the projects using this joint condition. And then you connect this with the employee with this condition. And finally, we make the project operation. But remember, there could be alternative ways to do the same thing, because in SQL also, we know the same query we can write in multiple different ways. So this is another way of writing. So in this particular case, it's coming from the different example. We have instructor, teacher, and the courses. We just combine these two, and then we will select only department name, music, and then we retain only the name and the title. The similar thing can be done by first select music from here, the instructor, and then we can combine both teachers and courses, and finally you combine the two, and we can select the name and title. Right. Now, one thing is drawing a query tree to identify what operations are there. So we have seen here, for example, project operation, select operation, join operation. So we have two join operations, right? So we need something called execution plan. What do you mean by execution plan? How exactly this is used for each of the operations. So how do you, make the project operation? How do you make the joint operations, right? So that is where we want to focus on here. Right. So you can see here in this particular example, so we can see that we have limited number of records here. And here we also limited the number of teachers based on the year. And then we'll make the change. And then finally, you join with the course. Right. What are the approaches for query optimization? One is we can say heuristics in query optimization. That means, from the beginning, if you have worked with, you have some idea like what might work well. So given a query, perform selection and projections as early as possible. And then the second one is you should eliminate the computations, based on these two topics. The second one is cost-based query optimization. That means we calculate some kind of a cost for equal query expressions, and we choose the best execution plan. So to begin with, starting with the heuristics query optimization, what happens is you usually start with the initial internal representation. So the query tree that we have already seen. And I told you there could be like multiple versions. And then you apply these heuristics to optimize the internal representation. And then third, you will have a query execution plan generated to execute group of operations based on the access path available on the first files involved in the query. So the main heuristic is in the optimization perspective, you should apply both select and operate, select and project operations, right? And then you can use select and project operations before applying the join or any other bind operation. So that means before you connect, you should be able to use select and project to minimize the number of participants. Right. So we already have seen some examples for a tree. Simply you represent all these operations as a kind of a tree. And the second one is you can also connect it to a query graph, right? So in this particular case, what happens, we want to, represent, and then we need to understand which operation we should perform first. Right, let me give you an example. So let's say every project located is Stafford, retrieve the project number, control department, the number of department, the last name, address, and the project, which exactly what we discussed early. So you can see both the relational algebra expression and SQL query. So having said that, now you can look at how it might connect the dots, which means what operations it performed. For example, if you look at the first tree, you will notice that, okay, you will limit the number of records belong to project, but what you need is project location, right? Same is with others as well. So always we compare and then we make the decision. So in this particular case, we want to combine both project and the department. So the joint condition is dnum and dnumber. And then you will have employee relation as well. You can directly meet, right? And then finally, you can select the results that you want, right? The second one is we are using cross here, which is called Cartesian product, which means all possible combination of this. This might work for a smaller data set, but will not definitely work for larger data set. Right. Let's look at in more detail about the heuristics in query optimization. So first one is the same query will be correspond to many different relational algebra expressions, and then you should get like different query trees, right? And the task of this optimization process is we need to find an initial query tree representation, and then that based on that we can make an effort to make slight changes. Equivalent SQL statement is also given here. Right. Now let's try to understand what are the heuristics that we can perform. So what you do is usually when you're given a SQL statement, you try to come up with this initial query tree. So one example is given here, right? We are connecting both employee works on and the project, and this is what we're expecting. Right? So the idea is you have pushed down all the three tables. We consider all possible combinations, and the results is also compared with the project, another combination, and then this will be the join conditions and also your birth date information like date operations. Another example, right? So you can notice that in this particular case, you will select employees who uh, works here after 1957, right? Then you combine with the works on and you match employee social security number, social security numbers in employee match with uh, employees social security number, and then uh, which is equal to um, social security number. And then we can talk about the connecting the project. Project will again connect to from that branch, and then we set in this particular case we want to set the join condition, right? By looking at the number of records, can you guys tell me which tree is the best? Is it A or is it B? Okay, now if you have very large data set, what we are doing is we are using Cartesian product. If you remember, Cartesian product means all possible combinations. When you say all possible combination, it will generate huge data set. And this is also the same. If you use these Cartesian product among the three relations, it will get huge records, and this is where we make the connection, right? Therefore, we need to optimize the query. So we should never use cross products. Instead of that, we have to make a cross product and we have a join operation. Simply cross product and applying the condition will be joining the two. But before that, we reduce the size of the employee table because we will remain or retain those who born after 1957, December 31st. So when you actually combine, you will get a small number of records. Similar to that, here, then this particular resource is connect with the project. So therefore, if you think about the time it takes to execute, your answer should be answer B, because you filter in the beginning. So you can see that when you write down SQL, you don't think in that way, but internally, database management system has to look after this number. Right. Next one. These are the steps of query optimization. You will start with the initial query, then you move down the select operation. You can see selection is moved down here so that you will have a smaller record or smaller set of programs. The second one is you apply select statement as well. So for example, we can see selection of project name, selection of whether the dates is greater than 1957, December 31st. Right. And then what you do is, once you identify this, I told you like the Cartesian product is not very useful. So we will use, instead of these, we are using join conditions, which is much better compared to our previous one. Okay. Next, having said that, once you do the project operations, so we did the selection, then we did the project operations, but that project operation can go down where actually it connects to each other, right? So that's what happens here. So you make the selection and then you select only one attribute. And then here we have employee social security number and another one. And with this, we can combine to each other. Right. Simply, we can list what we have discussed so far. right? So before we talk about query optimization, we need to start looking at what properties we have in the relational algebra operations. So let's say you have a cascade sigma. In this, what it means is there'll be a sequence of instructions or selections happens with the relation. And if you have, let's say you have a set of conditions, C1, C2, and up to Cn. So best place would be that you ask each and every relation, you apply this. And the second one is, when you're performing selection and after selection, doesn't matter. So you can look at the both in this particular case, and then you can actually switch and you can do this vice versa. Third one, project operations. So sometimes you can say, okay, the first name and last name, right? So if you want to retain a list of attributes, then you have to list it in this manner, which is not possible for increased data. So we need to restrict that one as well, right? And also, how do you commuting sigma with I, right? Only one attribute. Then there could be like two operations. Then commutatively, that means join operation or the Cartesian product. This is called commutative. That means, both R and S could be included in any manner. So it doesn't matter whether you have R or S, right? You will get the same result. Similar to that, commuting with join operations. So let's say you will perform join operation between R and S, then you make the select operation. It's the same as you perform for first the selection operation, then we have this, right? And finally, we can talk about this. We can actually make it particularly interesting by filtering out all the recording information. So if you have value here, so this will represent the join operation with the selection with C. So that means we can apply individually R and S, then you can perform the join operation. So that's what it means. Then if you have a join operation and then list of attributes to retain, so what you can do is you can apply these to both R and S, and then we make a join condition. Next, we can talk about a set of operations. Set operations, we can talk about the union, intersection, and the difference, which are almost the same. Then associative of, in this particular case, join, you can see order doesn't matter, assuming that these operations are theta. So we can say you perform R and S, in between we provide 0, and that will be connected to T. And then order doesn't matter, which means here we actually first performs join operation, right? Different operations. And then if you perform the same, then it is same as in this particular case, R S S together and T separately. Now you put R and then we work on S and T. Next, look at set operations. If you have a set operations, right? So for example, in this particular case, we are talking about the union, intersection, and difference. So you can have a generalized query. The theta could be any of these. Right. Then selection operation. Again, score commune. And then you can see instead of you are getting common modules, RNS, and then perform the selection is the same as you perform the selection, then have, right? In this particular case, a union which combines two queries together. Next one, select and Cartesian product, which be equivalent to our join operation. So if you get the Cartesian product and apply the joint condition, then we can say that, okay, they can take you, in this particular case, RNS. So performing Cartesian product and the selection is same as you provide the joint operation between RNS. Right. Now, using these optimization algorithms, we can actually break up any operations, and then we can use conjunctive conditions into cascade or select operations. We have seen that in some cases, you can apply one after the other, we call conjunctive, and then select. And then rules number 2, 4, 6, and 10, it's commutatively select with the other operations. Then use a rule number 9 associated. Rule number 12, you combine the Cartesian product operation with subsequent select operation. So that part also will cover. And then last use of rule number 3, 4, 7, and 11, cascading of project and becoming a project with other operations, breaking down, move list of project attributes down the tree as far as possible. So remember, we discussed this idea to limit the number of records when you want to combine the two relations together. 6, identify subtrees that represent a group of operations that can be executed by a single algorithm. Right, just to summarize what we have discussed so far, we were discussing how we use heuristics for algebraic optimization. So what we discussed, mainly you perform the operations before you reduce the size of the intermediate results. The second one, you perform the select operations, and then you reduce the number of tuples and performs the project after early as possible. Third, select and join operations that are mostly restrictive should be executed before other similar operations. So simply what you do is you usually reorder the relations. Okay, next, for execution plans. Now, once you see this, we need to figure it out how exactly you are going to execute this. So the execution plan for a relational algebra query, we have to have relational algebra query tree, which we have discussed early. And then what we need is access method, which means how exactly you connect to your storage device. So that's what we need to discuss. Okay, having said that, let me conclude today's session. And then I will share the video